Alrighty.
And there's my pen.
Good morning,
Good
afternoon,
morning,
or evening
physics.
So first big thing.
Let's talk about this
and how
and
I
how I
handle
handle
bigger notes when we're doing actual questions
with equations.
So I give you guys
the answer
and the units for it. So if I'm already giving you the answer, what am I grading?
It'll work.
So on these notes, first of all, make sure you put your name and date. And then let's also go and get this down. So we're talking about average acceleration. If you want to find average acceleration, here's what we gotta do. And we can write it like this: acceleration, which we assume that we say acceleration, it's the average acceleration. But I just put AVG as a little subscript, so we knew what it was. So our average acceleration is equal to our change in velocity. So delta, that's always going to mean change in. That means once again our change in velocity. And that's divided by time. So basically just a fancy speed divided by time. But it's velocity because it's a vector and it will work for acceleration. And that is our time. Once again, I write my t's to the side like that. So that way we don't mix them up for plus signs. So what does change mean? Our VF minus VI, our final minus initial. So all that means is final minus initial. I need to make sure that I have that for you guys. Awesome. So okay, now it should be fixed. That should fix everything. Yay. So once again, our average acceleration is equal to our velocity divided by time, and that's going to be our final velocity minus our initial. So on this very first question, we need to first define what all we have. We're looking for the magnitude of our average acceleration. So our acceleration is going to be our question mark. And now we break down what we do have. So it's going to accelerate from rest to this velocity, 17 meters per second. We know it's velocity because it's just in meters per second. And then finally, we have a time of 5 seconds. So here's what we got to do. Our first thing is we have to figure out both of our velocities, our initial, our final, and then we need to figure out our time. Good news is there's only one of these that we aren't given a number for. What does rest mean? 0. So if you ever see from rest or to rest, we know that we're putting 0 in the place of something. So for our initial velocity, that is 0 meters per second, and we are good with that. Then on our final velocity, that's going to be 17, because we end up at 17.0 meters per second. And our time is going to be 5 seconds. So we're going to plug this into our equation that we have up here. Our acceleration is equal to, make sure we rewrite it. That way someone can follow our process and figure out what we're doing. Our final velocity, which is 17 meters per second, minus our initial velocity of 0 meters per second. And we divide that by time of 5.00 seconds. That should get us a number very close to this. This is with significant figures, so we may be off by a hair, and that's okay. So just 17 minus 0, so 17, divide that by our 5, and we get 3.4. And it's meters per second squared because it ends up being meters per second divided by seconds. And we're golden. Make sure that once you're done, block your answer, and you're good. On this one right down here, it's the same exact process. Which one is harder? Let's start with this one because it's deceleration. So on this one right here, I'll have you guys do C on your own. But on this one, Once again, we're looking for our car's acceleration. So our acceleration again is our question mark, and we know what equation we're going to use. Same one as last time. Then we need to have our initial velocity, final velocity, whoops, and we need to have our time. Our time, once again, an automobile is moving along a straight highway in the positive direction, but the driver steps on the brakes. So if we're ever slowing down or decelerating, we have a negative acceleration, so we're going to get a negative acceleration from this. But let's talk about this again. The initial velocity is 15, and it takes 5 seconds to slow down to 5 meters per second. What is the car's acceleration? So our initial velocity is going to be that 15 meters per second, because initial just means starting velocity, or whatever you have at first. Then 5 meters per second for our final. Then 5 seconds. So our acceleration, this is always our average acceleration, is our final velocity minus our initial velocity divided by our time. Plug all these numbers in. This time it is going to be 5 minus 15. My bad there. So 5 minus our 15.0 meters per second divided by our 5 seconds. So first big thing we need to notice is it's 5 minus 15. This is going to equal negative 10 meters per second over 5. 10 divided by 5 is going to be 2. Negative 10 divided by 5 is going to be negative 2. Our acceleration will equal negative 2 meters per second squared. And once again, we have meters per second, and we're dividing by second. That's how we get meters per second squared. Try out C, and then continue with this video. So we have to break down our kinematic equations. These are in our notes already, or you guys already have access to them, but let's break it down anyway. First big thing, let's break down each of these variables. Our D, this may also be seen as X. This is our displacement in meters. And it may also be, some people will use X, or they'll use R instead of D for displacement. I prefer D because it makes sense. Okay, then the next big thing, we have our initial and final velocity. And this is, I'm going to go and write that out. Meters per second. And it doesn't have to necessarily be these units, but these are the units that we generally use for these questions. So sometimes we may have to convert a unit to make it work with the rest of the units we have. And then this can also be V node, or node V, or V0. Or also, my bad, it can also be V1, please pardon me. It can also be V1. And then for final velocity, they will use that as V2. So usually you'll see VI or VF. Those usually work the best. But you may see someone say V node or VI. Sorry, V1. Chakra meters per second. And you may see that as, we don't really have like another weird V thing for the, or weird thing. They may just use plain old velocity, and they may just also use V2. I've seen some people use like V and then the omega symbol, but that's incredibly rare. And not something you would normally see a teacher or professor do. Then we have our acceleration. This is once again how fast we are speeding up or slowing down. It's almost always A. And it's going to be in meters per second squared. And there's not really another unit to list there because we almost always use A for acceleration. If it's gravity, you might see G, but usually it's only for using gravity and we were just dropping objects like. So, I have the lag on that. So, with our time, that's going to be T. And that's usually in seconds. So keep in mind, if we decide to use another unit of time, we have to change all of these units and convert them. So if we are given hours and everything else is in seconds, it's better to convert this one unit instead of converting all of these to seconds. Same thing if you get meters and you're given kilometers instead, it's easier to usually convert that one unit than convert all the other things in your equation. Especially with some of these being rates that are complicated and require multi-step conversions. So if we're breaking these equations down, here's what this looks like. On this very first one, which is our d is equal to our vi times, and I'm just going to go ahead and write it out like this because we can see that it's multiplying. So vi times t plus 1/2 at squared. And this is why I do that big curve, because we have a plus sign and we have a t in the same equation. So it's very easy for people to mess up on these. So on this one, our displacement and then I don't want you guys to break this down. Whoops, plus. Let's skip going over these in words, because honestly, as long as we see this in the equation format, most of us already understand this process. But if we were to break this down, displacement is equal to the initial velocity times time plus 1/2 our acceleration times time squared. Don't worry about these boxes right here because I think that this is no longer something that is necessary. I use the same format back in COVID to help us out. But I think that we have it from here, just from these equations. So go ahead and just rewrite our equations. That way we have practice writing them once. And then VF is going to be equal to our, ooh, that's an interesting looking F, VI plus our acceleration times time. So just go ahead and copy those equations. We won't go ahead and do those in words. Just focus on go ahead and rewriting those equations once, just so we have the practice. Now here's where we actually get to do these kinds of questions. So we get to choose one of these equations to guide us on each of these questions. So let's label what we have. An airplane accelerates on a runway at 3.20, and that's an acceleration for 32.8 seconds until it's finally to lift off the ground. Determine the distance before takeoff. So we don't have the distance or displacement, so that is what we're searching for. So it may be best to find an equation that has this as what's already solved for. Then we want to label out what else we have. We have our acceleration, which is 3.20 meters per second squared. We have our time, which is 32.8 seconds. And then we also have our initial velocity. Because if a plane is speeding up and it has passengers loaded in it, we can assume that the plane is accelerating from rest. Because before takeoff, it's at rest. So we can assume our VI is going to equal 0. So our initial velocity is going to be equal to 0. We do not have our final velocity, as we don't know how long it will take for it to, or we don't know how much speed it's going to get up to before it takes off, but we have how long it will take. So we're going to come back here and snatch one of these equations. This one does not have final velocity. So we're going to use this first equation up here. I just labeled it 1, 2, 3, 4. We're going to use this first equation right up here. Our displacement is going to be equal to our initial velocity times time plus 1/2 acceleration times time squared. We need to not forget that time right there. So first thing we want to do is we want to plug everything in. Our displacement we're going to leave alone. Our initial velocity is going to be 0. So we're going to start off with 0 meters per second times 32.8 seconds plus, and then that's going to cancel this out because 0 times 32.8. 1/2 our acceleration, 3.20. I'm going to put our unit down here, times our time of 32.8. That's in seconds. So just rewriting down here, 1/2, 32.0 meters per second squared times our 32.8 seconds. We plug it in the calculator and we're golden. So just I'm just going to use 0.5 to make my life a little bit faster. 0.5 times 3.2, whoops, times our 32.8. Whoops. Oh, I just did the thing I told y'all not to do. That is squared. That is squared. This is also why I put this on here, because everyone can make mistakes. And there we go. We're going to have some these numbers which are slightly off. 1721 is around the same as 1720, give or take about a meter. We are looking more for just you guys having the math skills and practicing them. We're not looking for you guys to have perfect significant figures and everything. As long as you're within 1 or 2 numbers, you are good. And that's all we do with these questions. We need to first break down what we have, figure out what equation we need to do second, and then we just plug in numbers, and we may have to solve for one of these. A great example.
Good morning, students. The Tuesday talk video has been moved.
And there we go. Sorry about that. So we may have one that we have to manipulate algebraically. That just means that we may set up our equation and find out that it is a solve for x kind of equation. On this one, we're looking for time. This is number 5. So we're looking for the time. That is our question mark. And we have the height. So that is going to be our displacement, or our x. And once again, they're dropping a feather on the moon. All right, and our acceleration of gravity, that is going to be our acceleration. Our acceleration will be 1.67 meters per second squared. And then if we're dropping an object, it has no velocity right now. So whenever I do drop it, that's when it starts accelerating. So our initial velocity in this scenario, if you ever drop an object, it starts off not moving. And this is when we have to make a decision on how we want to do this. I'm going to go find an equation that has all of these and not final velocity. That's my first equation. And here's how it's going to work. We're going to have to plug it in and see if this will work, because we don't want to have some weird thing going on. Our initial velocity times time plus 1/2 acceleration times time squared. Here's a problem. We have two different times. Let's plug in numbers and see if one of these will go away. Our initial velocity is going to be 0 meters per second times our time, which we don't know, plus 1/2 our acceleration of 1.67. That's going to be meters per second squared. And then that's going to be times our time squared. And we don't know our time yet. And we also have our displacement. So this is going to get swapped out for 1.40 meters. So at this point, we're crossing out of this section. We have our d, 1.40 meters, is going to be equal to 1/2 times our 1.67 meters per second squared. And then that's going to be times our time squared. Now we're just solving for x. We're going to divide off both of these, and we are going to square root this part, and that will give us 1.29 seconds. Finish out this question, and if you have trouble with it, come see me.